Welcome to another lecture. We're gonna look at the identity theorem. It's one of the most basic theorems about, well, in the end, holomorphic functions, analytic functions. That's really something about having a power series. So this is section 2.4.4, so subsection 244. All right. So, well, let's just state and prove the identity theorem. So, suppose that we have a domain. Here it's important that it's a domain that's connected. That's an important thing. And suppose that we have an analytic function. So a function which has a power series at every point. Right? It's equal to a power series in some neighborhood at every point, right? That's what analytic means. Now let's define this set ZF be the set of zeros, the set of roots, the set of points where f is 0, right? And let's suppose that this set has a limit point in U, right? So there's some sequence of these points. You don't have to take all of them, just some sequence of them. And this sequence has a limit, and the limit is inside U. So it can't be on the boundary, it's inside U. Then f is identically 0. All right. In other words, and this is still an important in other words, all points of this set are isolated. So all zeros of f of a holomorphic function are isolated unless the function is identically 0. That's well, if we're talking about a domain, right, connected, right? If you have a disconnected set, it could be identically 0 on one component and not on another one. All right, so yeah, I guess I already, gave this definition. We call these zeros, and we're gonna look at the zeros of holomorphic functions often. And we study these a lot. Now, a common application of this theorem of identity is that if the function is 0 on a non-empty open subset, then it's identically 0, right? So if it's 0 in a neighborhood, it's 0 everywhere. Now, that's stronger. I mean, that clearly has a limit point, right? A non-empty open subset, yeah, there's a lot of points, and they all have limit points. A lot of limit points, right? That's what I mean. So that's that's clearly follows from that, and that's probably like 90% of the applications of this identity theorem is that you find, well, I have these two functions and they're equal on some small open subset, therefore they're equal everywhere, right? That's the biggest use, right? By the way, I'm saying saying two functions equal, even though this is something about something being 0. Well, two functions are equal, subtract the two functions, right? If I'm supposed to, f is equal to g, that's the same as f minus g is equal to 0, right? So any equality is always, you can always rewrite any equality as something equals 0, right? So anything about solving some equations is always solving something is equal to 0, right? All right, so that's what we're trying to prove. So let's prove it. Suppose that f, this holomorphic function defined on this domain, on this connected open set, is not identically 0. So there's some points where it's not 0. Now, it's continuous. It's holomorphic, it's continuous. So the set of zeros is a closed set. It's a pullback of a closed set, right? Because the 0, just the singleton point, is a closed set. Its pullback is going to be a closed set. Now it's closed in the subspace topology on U, right? So it's not closed in C as a closed subset of C, right? That's sometimes the tricky thing that you have to that you have to think about here. So it's closed as a subset of U in the subspace topology of U. All right. Now, what we want to show is that all the points of f are isolated. All right, well, let's let's go sort of from the other side, right? Well, suppose that I have some 0, right? And let's suppose that it's at 0. So f of 0 is 0, right? So that's what I'm saying here. And let's suppose that 0 is not in the interior of this point, right? Just if of this set, of the set of zeros. Because if it is in the interior, then f is identically 0 on a neighborhood of 0 in this case, right? So let's not worry about that for now, right? We'll show that yeah, those points can't really exist if f is not identically 0. We'll show that later. So let's suppose now that we're not in the interior, right? So in any neighborhood of 0, f is not identically 0, right? It could be 0, maybe we don't know right now. It could be 0 on lots of points, but it's not identically 0. That's what we're basically saying, right? So let's write down, it's an analytic function after all. So I mean, this whole identity theorem is really because it has a power series, right? So identity theorem is something about analytic functions. So let's write down the power series, right? There's some power series at 0. Now, because f is 0 at 0, right? This is a 0 of f. There's lots of zeros in this proof, right? 0 is the 0 of f, right? I mean, it sounds stupid, but that's what it is, right? So f of 0 is 0. It is a 0 of f. So C0 is 0, right? It's just all sorts of zeros flying around, right? So that means the first coefficient is 0. Well, maybe a whole bunch of them are 0. Maybe not. Maybe just C0. Maybe C1 is non-zero. But maybe C1 is 0. Maybe C2 is non-zero, or so on, right? Suppose that we take k to be the smallest k such that ck is non-zero, right? Now, whenever you say something like, well, let this be the smallest k such that ck is non-zero, you have to think, well, does that exist? You can't just take it if it doesn't exist. But here, it has to exist. Why? Because f is not identically 0 nearby, right? So if the smallest k didn't exist, that would mean that ck, Cn is 0 for all n, right? Well, that would mean that f is identically 0 nearby in a whole neighborhood of 0. And we know that that's not true. So there has to be at least one k, so that ck is not 0. So make it the smallest one. Now, and this is a really useful idea. So what does that mean, right? That means that I can, every one of these, this really starts at k, right? So every one of these powers over here is, is bigger than k. I can factor out a z to the k out of all of these powers, right? So I can write down this power series over here like this, right? I can factor out a z to the k, which there's nothing about conversions here that breaks. So yeah, that's still true, right? And what do we have left? Well, the thing that's left, this part, is just the power series, right? I've taken out some of these powers, but n was always bigger than or equal to k because, for all n less than k, Cn was 0, right? So those guys really weren't there. So there's no I didn't really write, I don't have some 1 over z or something like that, right? I mean, this is an honest power series, right? So let's call it G, right? That's that power series. It converges on the same set as f, right? So it also converges on a neighborhood of 0, right? So conversion power series. And G of 0 is ck, right? Because that was the smallest smallest coefficient which was not 0, right? So that's now the constant coefficient after I've divided by z to the k, right? And that's not 0. So G is not 0 at 0. That's really what I worry about here. Because what does it mean? Well, G is continuous. So convergent power series is holomorphic. It's much better than continuous, but it's definitely continuous. So we have a continuous function. It's not equal to 0 at 0. So it's not equal to 0 in a whole neighborhood. There is some neighborhood, maybe only a really small neighborhood, but there's some neighborhood where G is non-zero, right? Or it has no zeros in that neighborhood. Z to the k, on the other hand, well, that's not 0 for any z that's not 0. That's only 0 at 0, right? The only way I can make z to the k be 0 is letting z be 0, right? Well, so that means that if I multiply z to the k and g, then on that neighborhood where g is non-zero, the only possible 0 is 0. That means that f, which is this product, is, has an isolated 0 at 0. All right. So what did we prove? We proved that we started with a 0, which was not in the interior of this set Z of f, and we showed that it is isolated. So that means that points of Z of f are either interior points or isolated points. There is no other possibility, right? So let's, let Z prime sub f, I have to, make up some notation for this. Let those be just the interior points. Just the points that are on the interior of this set, the interior of this guy, right? So the non-isolated points. Now, this is a closed set in U, right? In the subspace topology. Why? Well, this guy, the ZF, all the zeros, that's a closed set, and the isolated points, right? Those I can subtract those and still have a closed set because I cannot approach from from the interior. I cannot approach an isolated point. Another way to see that this is a closed set is that well, the isolated points lie in an open set, right? I can just always put a little. That's the whole point of being isolated, right? I can put a little neighborhood around each one of those points that doesn't hit the rest of the set, right? And so I can subtract an open set to get Z prime, right? So if I have a closed set, they subtract an open set, I get a closed set. All right. So in any case, because it's the interior, it's an open set. It's also closed. So it's open and closed. It's a subset of U. U is connected, right? So therefore, U is either equal to Z prime, which means it's equal to ZF. That just means that F is identically 0. Or Z prime is empty, meaning all the zeros are isolated, right? Z prime are just the interior of the zeros, right? So good, we're done. So either it's identically 0 or all the zeros are isolated. Now, before we go, there's a very useful idea in this proof that we're going to use over and over, and you probably want to use over and over. If you have a power series, and it's really about power series, but it's going to be about holomorphic function, analytic functions, whatever. If you have a power series expanded around A, and this power series has a 0 there, right? So the 0th coefficient is 0, right? Then we can factor out some power of z minus a, some actually positive power, z minus a or z minus a to some higher power, right? you can always write down something like this. And if this was actually 0, then this k is at least 1, right? We can at least factor out one of them, right? And we can factor out enough of them so that g is non-zero, right? Well, I guess I'm assuming here that f is not identically 0, right? But that's a very useful idea, right? That's something that we will keep using. All right. So next time, what we want to look at is we want to start looking at the line integrals. So we're going to move to chapter 3. All right. So see you next time.